Hi viewers, welcome to LMS Solution. Today we are going to see about solar PV battery integrated UPQC system in Matlab. Thanks for watching our videos. Kindly subscribe our channel and also click bell icon for notification about upcoming video. Let's start with the implementation of solar PV battery integrated UPQC system in Matlab. So this is the model of PV battery integrated UPQC. So here you can see that. So this solar PV rating we are using, that means we are using 18 series connected string and 28 parallel connected strings, and each panel having 213 watts, and then voltage at maximum power point is around 29 volt, and current at maximum power point is 7.35 amps. So here you can see the PVAV characteristics. The maximum power is around 107.4 kilowatt, and then voltage, operating voltage is around 522. Okay, so the voltage will be vary in between 522, so in between 500 to 505 to 525. Okay, and here we are using that the boost converter. So here we are going to maintain the DC link voltage around 700 volt. Okay, so we need to design accordingly based upon the power rating. So for that I'm going to use this detail, right? The input voltage of the solar PV I'm going to consider 552, the maximum voltage level, and then output voltage is 700, and then the power rating is 107.4 kilowatt, and then so this is a calculation used for calculating LNC value for that boost converter of solar PV system. So here you consider 3 millihenry, and then around 6600 microfarad capacitor. Okay, so that value used here 3 millihenry, and then the capacitor is around. I'm choosing more than that 6600 microfarad. Okay, and then here you can see that we are using P and O MPPT. Okay, so in P and O MPPT we are using measuring the power of PV voltage and current. So based upon that PV voltage and current, we are generating the reference voltage. So this is reference voltage, nothing but not reference voltage. So this is nothing but duty cycle. So we are generating a duty cycle. So when you go inside the P&O MPPT, you can see the code. So this is a P&O MPPT code. So it will generate a duty cycle. The duty cycle can be processed via PWM generator. So this PWM generator is drive the IGBT in order to extract the maximum power from the PV panel. So next we are going to see about the battery section. So in battery section, right, here we are using battery, the rating is around, once again, yeah, we are using a 24 volt battery with a 20 series connection, and capacity is 48 Ah. Okay, and the initial state of charge we are consider is 50%, and then is going to be connected with the PV system or a DC link, right? So it's going to be connected, the battery going to be connected to the DC link via this bidirectional converter. So you have to design the value for L and C. Okay, So for that, I'm going to consider this equation. So here the voltage of the battery is we are taking 20 into 24. The power rating is going to be taken as the same as of the solar PV system, and switching frequency we are consider as 10 kilohertz. The DC link voltage is 700, and then we calculating the value for L and C for that bidirectional converter. So this is the value for that bidirectional converter L and C. So 0.1124 and 4.5 e power minus 5. So that value going to be used here. So 0.1164 and 4.8 e power minus 5. Okay. So I'm taking a little bit higher than that of the designed value. Okay. So here you can see that we are measuring that DC link voltage. So here we are measuring DC link voltage here, right? This one measured here and then compared with 400 volt, and then it's going to be processed via PA controller. So it will be generate the reference current for the battery charging discharging, and then here we are measuring that battery current, and then it's going to be processed via PA controller. So the PA controller will generate the duty cycle, and duty cycle going to be processed via PWM generator. So it will be generate the pulse for this bidirectional converter. So is given to here, right? So it will be maintain the voltage across the DC link, okay, and also reverse the current flow, or that means it going to change the current flow according with the rating of the power availability of the PV, okay, and then power requirement in the grid side, okay. So next we discuss about DC link, that means a shunt converter and a series converter. So this is known as shunt converter, and this is known as series converter, okay. So here I'm going to control the shunt converter, so by using this logic, right? So that means again we are going to measure the DC link voltage, and it's going to be compared with the 700 volt, because we need to maintain the DC link voltage around 700 volt, and then it's going to be processed via PA controller. So it will generate a power loss. So here we are going to use the PQ theory concept, okay. So by using PQ theory, we are going to generate the components or reference current for controlling of that shunt active filter, okay. So for that, here you can see that, so this is a control. First you have to measure the DC link voltage and then compare with the reference voltage, and then process via PA controller. So it will generate loss power, and we need to measure the grid voltage and then load current, okay. So inside we go inside. So based upon that grid voltage and the load voltage, next you have to apply that you have to find out the zero sequence current, power, and actual power and reactive power, okay. So here you have to just you have to apply that transformation, right? Alpha beta zero transformation, right? Just you have to calculate zero voltage alpha, v beta, and then you have to calculate current, zero current, alpha current, beta current, and then you have to calculate zero sequence current, and then you have to calculate power, real power and reactive power, okay. So this is going to be used for calculating that real and reactive power and zero sequence power. So next you have to that the actual power, right? It will be processed via low pass filter, and then is again compared with that actual power. So here you have to filter out the noise, filter out the that means you are going to take the average value of that actual power. So next you have to compare with the last power, right? So you have to subtract the last power from the actual real power after filtration, after low pass filter, okay. And then we are taking the same value of I naught and P naught, and then you have to take the value of PE after subtraction of loss power, and then you have to take the reactive power, and then you have to take the actual voltage, that the source voltage. Okay, next you have to generate the reference current. So here we are going to again you have to calculate that zero voltage, alpha voltage, and beta voltage by using this formula, and then you have to calculate I alpha, I beta. Okay, so based upon that real power, reactive power. Okay, so from the previous block, and then from that after calculating I alpha, I beta, and then I zero, right? So we need to calculate IAC, IBC, and ICC. So this is known as a reference current for that next stage. Okay, reference current, or else we can call it as a compensation current, right? So this reference current will be taken, or compensation current will be taken here, right? And then it's going to be compared with the current from that shunt active filter. So here we are measuring that current, right? ICOM, right? So you have to compare with that shunt converter current. Okay, just you have to compare that the compensation current with the current of that shunt converter, and then it's going to be processed via hysteresis controller for generating the pulse. So it will be generate the pulse. So here we are taking the 6 pulse. So that means, so directly you take the direct pulse, and then you have to take not logic, and then you have to generate the 6 pulse. Okay, so this 6 pulse going to be control the converter, shunt converter, right, in order to compensate the harmonics. That means if suppose any harmonic available in the load side, so it's going to affect the source current, right? So we need to avoid that problem, right? We need to make the source current sinusoidal. So based upon this control algorithm, you can easily mitigate the problem. That means harmonic current in the source that can be mitigated by means of this attractive filter. So for that purpose only we are using that PQ control concept. So next we move on to series active filter or series converter. So normally series converter connected to the system via this transformer. Okay, so the converter going to be connected the series with that grid side. So use of this series uh, converter or series active filter is to mitigate the problem in the uh, grid system, like any sag or swell occur in the system, right? So that going to be mitigated by means of this series action filter by means of injecting the voltage into the system. Okay, so based upon that the source voltage and the load voltage. So here we are going to measure. So this is a control logic we are using for that series converter. So here we need to measure load voltage and then source current. So that should be converted to dq naught, and then the load voltage going to be compared with the source voltage. Okay, and then this source voltage compared with the reference voltage. After that comparison, this error voltage and this error voltage going to be compared here, and this error voltage and this error voltage going to be compared here. So final error voltage, right? The final error voltage will be processed via PA controller. The PA control will be generate the control voltage in the form of DQ. So that the DQ form will be converted to the APC form by using this transformation DQ not to APC, and then it's going to be processed via reference. That means PWM generation block. Okay. So for example, we consider if both voltage, load voltage and source voltage will be equal, right? So this the error voltage will be always 0 here. But after comparing, here error will be 0, here error will be 0. So after comparing with the reference, right? So reference nothing but we have to compare with that peak amplitude, right? So this is not known as peak amplitude. So we have to compare with peak amplitude. So error will be 0 here, right? So normal case, no problem. After summation block, the error will be always 0. Okay. But for example, any that mean sag and swell will be occur in the grid side voltage, right? What happened? So this error will not be zero. This error will not be zero, and this is error also will not be zero, right? So if it is it's some errors similar to the PA controller, the PA controller going to be generate the compensating signal based upon this error voltage. Okay, so that compensating voltage going to be converted into actual ABC form, and then it's processed via PWM generator. So it will be generate the pulse for that series active filter or series converter. So based upon that error voltage, then pulse from that PWM generator, so it will be inject the voltage to compensate the voltage sag and the mitigation in the load set. Okay. So any deviation there, that means voltage sag also will occur in the system. Because of this shunt active filter or shunt converter, what happened? The load voltage always maintain at 1 per unit or a rated voltage. Okay. So for that purpose only we are using this shunt active filter, and then here you can see that on the grid voltage we are considered as 450 hertz, and then here we are creating that sag and swell here. Okay, so here you can see that amplitude will be 1.81 1.2 0.5. So here you can see that the time value for a sag and swell will be 0 1 1.2 1.4 1.6. So here we are mentioning that uh, the sag and swell condition in the source side, and here we are creating that unbalanced condition, right? So when the unbalanced condition is created, right, during the time also source voltage should be maintained at the sinusoid. Okay, so unbalanced condition will be created in the load set. And also here we are using nonlinear load, right? Diode rectifier load with the RL load, right? Diode rectifier with the RL load, so it will be create the harmonic in the source current, right? So because of this shunt converter, right, the source current quality going to be improved. Okay, next I'm going to explain about the results, simulation results. So here you can see that so here the sag will be occur, right? So because of sag, what happened, right? The series converter is injecting voltage into the system in order to maintain that load voltage at the rated value, right? So here the sag will be removed from the grid side, so then the system will be comes to normal. So that's why the shunt converter not injecting the voltage in the system. Okay, so here you can see that now the swell will be occur, right? Voltage swell, right? At the time of 1.4 second, right? So because of voltage swell, right, the grid voltage is increased some amount, right? Around 1.2, that means 0.2 percentage extra from the 1 per unit, right? But you can see that the load voltage maintain always 1 per unit. So here you can see that the shunt active filter, sorry, series active filter or series converter injecting voltage now to reduce that voltage of increasing voltage. That means because of voltage sag, right, you need to reduce the voltage level in order to maintain 1 per unit to the load side, right? So it will generate some reverse voltage, and it will going to be injected into the grid system, and it will be maintain the 1 per unit voltage at the load side. Okay. And then here you can say this is grid voltage, grid current, and shunt inverter voltage and shunt inverter current, right? So this is shunt inverter or shunt converter voltage and current. So this is the injecting current into the system in order to make the grid current sinusoidal. Okay, so here you can see that the load voltage is non-sinusoidal, right? When you got to expand this one, you can see that so load voltage is non-sinusoidal, but you can see that grid so load current is non-sinusoidal because of nonlinear load, right? So here you can see that the grid current is sinusoidal. Okay, so what happened on the shunt converter injecting the harmonic compensation current, okay, into the system in order to make the grid current sinusoidal. So that current harmonic problem because of nonlinear load is going to be is mitigated by means of this shunt inverter or shunt converter in the system. Okay, so here you can see the now we can see that so because of sag, right, the voltage is injected by means of series converter. After removed, that means sag will be uh, not occur in the grid voltage, right? The series converter is not supplying the inject the voltage into the system. Okay, is stop injecting the voltage in the system because there is no sag or swell problem in the system. So this is working of that solar PV battery powered or integrated UPQC system. Okay, so now that the irradiation is reducing, so because of irradiation reducing, what happened? The PV power also reducing, and also you can see that battery detail here. So we're using battery here. So here you can see that, yeah. So initially that solar PV having higher amount power, right? So because of that battery charging mode, okay. Now the PV power is keep on reducing because of reducing irradiation. So that's why the charging current is reducing. Okay, the PV now that's based upon the solar PV power. The battery going to be in the charging mode and are in the discharging mode condition. Okay, so this is the working of three-phase solar PV battery integrated UPQC system. Thank you.